Okay, so let's start by reviewing what we learned last time. The basic definition of probability space. The properties that the domain should satisfy. And there is a fancy name for this, for any set of sets satisfying this property. It's called sigma algebra. The sample set is in it. It's closed on the complement, closed on the union. It's called the sigma algebra. And for the probability function, we have three properties: non-negative, probability of normalization, and the probability of union of disjoint events equal to the sum. Okay. And then for set theory, we looked at the basic operation of union, intersection, complement. And we only have one formula, De Morgan's law here. When you move complement into each element, everything reverse. So union reverse to intersection. Okay. Properties of B. So these are some useful formulas to help you do calculation. One is probability of empty set is 0. And if you want to calculate this guy, it's probability of E minus its intersection. And this is a very trivial formula, but it's often very useful. It can simplify your calculation. Okay. Oftentimes, when we need to know this guy, we only know its probability of its complement. You can start with this one and have an easier way to calculate it. And the union bound, if the events are not disjoint, then you can have this union bound or exact formula. And some continuity. So recall the continuity in calculus. In calculus, you map, it's a function of number, right? You map number to number. And when you define limit, it's the number, the distance of the input is going to 0, and then the output of this function converge. Here we don't have a distance defined on sets. Okay? So this is not the same kind of calculus. It's a different kind of calculus. And we don't have a limit defined on the sets, but we can represent it using this one. So A is the intersection of all sets. This is not a distance measure, but it's a limiting intersection. Okay. So similar thing, we have a continuity from below. And we will continue today. I will give you a more elaborate formula for that, for this case. So let's look at what happens if you need to calculate E1, E2, E3, E4. What happens if you need to calculate the, so this is, let me see, so this is the 8th formula. What happens if you need to calculate union of all the sets? Okay. And if you recall this one, this formula is summation minus its intersection. Okay. So if we have 3 events, so let's look at 3 events example first. E1, E2, E3. If you look at the summation of all of them, then this part is counted twice, right? And this part is counted twice, and this part is counted 3 times. Okay. So the general formula is that we can just sum them together. Okay. And minus okay, this means intersection. Okay. I'm going to, because I summed them together, I'm trying to minus the intersection. Okay. So if I minus this intersection here, minus intersection here, minus intersection here, well, the middle times was subtracted 3 times, right? Here it's subtracted 1 time. That's the right thing to do because I counted this twice. I just need to subtract it once. But here I counted it 3 times. Now I subtracted 3 times using this formula. What should I do? Add it back, right? So the formula would be you have minus and plus, and again, the general formula is R plus 1, I1 less than I2 less than IR, probability EI1, EI2, EIR, and the last item is this guy. Let's see if we so we're union n events. Okay, so let's say if r equal to n, what happened? If r equal to n, it's here, and for n events, there's only one order possible, right? You're totally n, and you list all n number, and you insist it to be increasing. There's only one possibility, right? Here you have how many possibilities?
N minus.
This is n choose 2 possibilities over here, right? So if you have 3, if n equals to 3, you have 1, 2, and 1, 3, and 2, 3. You're doing the summation over here, right? And here, you have n, and you list all of them in increasing number. That's only one choice. It's 1 to n, E1, E2, up to En. Okay, so this is a general formula. You will rarely be able to use it because you rarely know the intersection of all of these guys, probability of intersection of all of these guys. Okay. So it turns out in practice, we just use union bound more often than this kind of exact calculation. Okay. let me ask you the flipping two coins. Okay. So suppose you have two fair coins. You flip the first one, you get head. What's the probability that you get head again in the next flipping?
1/2.
Half. Okay. So this is essentially you're doing two experiments, right? And when I ask you the question is, I'm asking you essentially the conditional probability. Condition on the first coin is 1. What's the probability? Or is head? What's the probability that the next coin, next flipping, give you head? Okay. For this kind of thing, when you have multiple experiments, you need to construct an overall experiment. Okay. So I will give you an example here. The sample space, what's the sample space if I flip two coins? So for one coin, the sample space is head or tail, right? So for flipping two coins, what's the sample space?
Head, tail, head.
How do you write that for each element? You can write it like this. Is this the right way to represent the outcome of the overall experiment?
The middle two be equivalent?
Yes, that's a problem here. The set doesn't preserve order. And I don't know which one. So if I look at this, I don't know actually which is the first from the first sub-experiment, which one is from the second sub-experiment. Which math object preserve order? Vector. So I need to change them to vector. Okay. So when you have multiple experiments, you should construct an overall probability space with the sample space include all the experiment outcomes. Okay. And how about so for one coin you have this guy. For the sigma algebra, the domain, it's I should use distinction here. So it should have empty set, omega 1, and head and tail. Is this a sigma algebra? What do you need to check whether this is sigma algebra?
Sample space is in the
Sample space is in it
closed under.
and closed under complement. This guy's complement is this, this guy's complement is this, this guy's complement is this, and this guy's complement. And closed under union, right? So union of any of these guys is over here. Union of H and T is omega, right? So this is a sigma algebra. How about this guy? When I combine these two experiments together, how many sets are there? It should include this guy, right? And should also include this guy, right? This is the event that the first coin is head, the second coin is head. We should be able to talk about this event, right? So, how many possibilities are there?
2:4.
So, if it looks from here, this is all possible subsets of this one. And for this coin flipping, we know the outcome of each one. So we can talk about the events of every outcome. That means this set is going to be to include every possible subset of this one. For subsets, if you assign an indicator of 0, if 0 means this element is not included in that subset. If 1 means this element is included in that subset. So for example, if 1, 0, 0, 0 mean 1, 0, 0, 0 means this guy, right? Means this one is included in that subset, and the rest is not. So assign a binary indicator for each element. You can enumerate all possible subsets. And the number of possible subsets is essentially the number of binary number you can have. So we have 4 bits here. The total possibility is 2 to 4, right? Is that right? So this could be so there are essentially this is all possible subsets. All possible subsets of omega 2. And there are 16 of such subsets. And we can use this notation. This notation is related to that indicator, binary indicator. Okay. All right, how about P? For P1, for this probably one coin, the probability space is, for example, if it's fair coin, you end up with this knowledge, you can calculate probability of every of these subsets, right? What's the probability of omega 1? It's 1. It's just this guy add together, right? All right, how about P2? What's the probability that you get head and head?
1/4.
How do you get that?
You have 4 outcomes.
Individual. Disjoint.
Disjoint?
Independent event.
Independent. What's the events? You are talking about the independent events, right? So what's the events?
Getting a head on one coin and down.
Okay.
Getting a head on another coin.
Okay, and then multiply them together. So essentially I'm looking at this one. Okay. So how do I get this? And this is I'm using the probability of I'm using probability of H. Let's change to this so that it's clear. calculating my new probability function using the probability function of the individual or of the sub-experiment. Okay, and the reason that I can do product here is that the two coin flipping are independent experiment. Right, I'm combining two independent sub-experiments together. Then I can use this product. Okay. So I will give you a formal general definition for combining multiple independent experiments. Okay. So this is how to combine multiple independent experiments. Okay, so if omega I, so when you talk about experiments, these three elements is enough to represent that experiments. Okay. So essentially, you know the outcomes, you know the probability of all the relevant events. That's all you need to represent that experiment. Okay. So if these are probability space of independent experiments. What do I mean by independent experiments?
The outcome of one experiment won't affect the outcome of the other.
So the outcome doesn't, so for example, next experiment doesn't depends on previous or future or the any other experiment's outcome. Okay, so if under this independent assumption, then the probability space of the overall experiment is omega, which is defined as omega 1 omega n. And omega are sets, right? I'm doing product of sets. I will explain what's the definition of product of sets. Anyone know? Probably product of sets. Okay, Cartesian product. And F, the overall domain of the probability function, is also represented as a product. And the definition is the sigma generated by A1 multiply up to AN and AI Okay. And we don't know what's this guy yet, right? We will look at each of them after I give you the overall thing. And for P, I'm going to define it in this way. If A is equal to A1 multiply A2 multiply AN, then PA equal to product of PAI, PIAI, PIAI. Okay, and this would produce a P. And it's represented by P1 multiply P2 multiply Pn. Okay, so I'm giving you how to combine them together, and all of this needs to be further defined. Okay, so let's start by one. If you look at this example here, this guy is essentially omega 1 Cartesian product omega 2. Okay, here is my definition of product of sets. So, definition. Let me go to the next page. Definition. A product B, A, B are sets. It's defined as a vector. A is in A, B is in B. Okay, so the definition of product of two sets is the set of vector. The first element of the vector is from the first set, second element is from the second set. And look at, let's go back to check whether this is right. This is a bunch of vector. The first element is from omega 1, second element is from omega 2, which is equal to omega 1. These two experiments are identical, right? I'm using the same sample space for them. So this is a bunch of vector. If you have n sets, what do you have? What kind of vector do you have?
N-dimensional vector.
What's the dimension of the vector? N-dimensional vector, and each one is from this. Okay. So essentially, I'm using a vector of outcomes to represent the overall experiment outcome. Does that make sense? That's the right choice for combining experiment, right? Okay, how about this guy? This is a product, but each of this guy here is a set. This is a set of sets, right? So what do you mean by this? And it actually means the sigma algebra generated by this one. And first of all, you know these guys I just defined for you over here, right? The product of A1 up to AN. You have a bunch of vectors. And this AI needs to be in Fi, so needs to be in its own domain. Okay, using I's experiments probability functions domain. And after you have this one, you have a bunch of subset. You have a bunch of sets of vectors, right? Actually, this itself is a set of n-dimensional vector. And this whole thing have many such sets. And a sigma algebra generated by it, it means this sets needs to be in this one. And also this guy needs to be closed under complement and the union. And also the omega, this guy needs to be in it. Okay? So these are just some of them, and then you can produce many others by doing complement and the union, and you put them in here, and it become closed. Then you have this new sigma algebra. Okay. Let's use this example to see. Okay. So for this example, flip 2 coin. Two coins. Continue. Oh, I should put it down over there. Flip 2 coins, and so we're trying to construct this F. To make it consistent with the definition later, I'm going to use this one here. So omega 2 equal to omega 1, F2 equal to F1, P2 equal to P1. So I have two sub-experiments here. Flip one coin, flip another, and they are identical experiment, but independent. Okay? And the overall experiment for the F, let's look at the F.
Excuse me. Say identical when all the omega, F, and P are same, right?
Yeah. It means the three elements of probability space are the same. Okay. So let's say, so essentially this definition says F needs to include all of these guys. Okay. So F needs to include the Cartesian product. Okay. So let's first just using some example. Head is a part of my F1, right? And T is also part of my F2. So the Cartesian product of this is actually only have one element. So this guy should be in F. And omega is also in F. So it's omega 1 multiplying omega 2 and equals to, this is HT product of HT and equals to head, tail. Tail, head. So I take one element from each set, make them into a vector. Oh, should write vector here. Head, tail, vector. And tail, head, vector. Okay, so this is another set that should be included in F. Okay. So you just keep doing this. Well, let's actually see whether we can just exhaust them. Let's see. We can also do this guy, right? TH. Any other possibility? So I'm taking all A out of its own sigma algebra and make product. So I already take this guy out, right? I also take this guy out, and I can also take empty set out. That will give you empty set. And I also take this guy in the F1, take omega in F2, omega 1 or omega 2 in F2. So let's do this. The empty set is over there. You can also do H times omega 2, which is equal to H times H or T, and equals to H. Take one element from here, another element from here. What's the next one? H, T. Okay. So I have these guys. I can also do T omega 2, right? And this will give me T H T T. I can also reverse the order, so omega 1 times this one, and also omega 1 times T. Okay. So it will be H, T, H, T, and T, T. Have I exhausted all possibility here? So let me write F2 here so that we can look at all the possibilities. So I take this guy, get empty set. Actually, this guy with everybody's empty set, right? And omega 1 with this is empty, omega 1, omega 2, omega 1 times omega 2, I did it. Omega 1 times h times t, I did it, right? And h times omega 2, I did it. H times h, did I do that? H times h, I haven't done it. H, T, T, H, T, T. Okay. All of these guys. So H, T, and then T omega 2. Did I do that? T. I have T omega 2, right? I did that. T omega 2, TH, TT. TH, TT. Okay, I did all of them. How many sets do I have here?
10.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Do I have all of them? Is this a sigma algebra yet? So we said this product means sigma algebra contains these sets, and it needs to be a sigma algebra, right? Are these sigma algebra yet? Is it closed under complement?
We don't have samples.
Can you give me an example that I will let you observe? Is it closed under complement? For example, the complement of this guy. What's that? Omega is this guy, right? Let's say that element is HT. So complement of HT should have HH, TH, and TT, right? Is that set in here? Which set has 3 elements? It's not here. Okay. So just by doing the Cartesian product of these guys, subsets of elements of F is not enough. We also need to put their complements in it, right? For example, I need HT's complement in it. Okay? Or, for example, I also need this guy and this guy's union in it, right? So, it's so as long as, so it should be the smallest sigma algebra that include all the A's. Okay. All right. So now you have the domain of these guys. And how about probability function? Probability function, we say that if A is a product, then PA is also a product. So let's look at it. So these are the product, right? So let's look at two of them, this guy and this guy. So probability of HT is equal to product of this one, and then I can use P1 of probability of H times P2 probability of T, and that give me, okay, so in English it's probability that the first coin is H, so is head, the second coin is tail. Okay, so let's look at how about this one? The probability that the second experiment. So let's do this. So and let's try to do a reverse translation. No, this I need TH here. I'm looking at this guy. Okay. How do you translate it into English, this event? Can you use a concise English?
Probability that first coin is either head or tail, and second coin is always head.
Probability of at least one head.
It's just the probability of the second experiment is head. Second sub-experiment give you head, right? I don't care what's the outcome of the first sub-experiment. So probability of event second coin is leaves head. Okay. So, and for these events, you can use this to, if you recognize this is then you can use individual experiment. So first, you tell me, first give me a number. What's the probability that second coin flipping give you head? 1/2. Let's see whether after we go through all this labor, whether we get 1/2. Okay, the probability of omega 1 is 1, right? Times this guy is 1/2. Finally, we get the same answer that you already get through your intuition. Why do we do this? Is it a waste of time? We go through all this labor to get such simple answer that you already know beforehand.
It helps us in solving more complex problems.
Right. When you have more complicated cases, then you have a systematic way to find your answer. Okay? All right. But what happened to this guy? This guy cannot be represented as a Cartesian product of some sets, right?
1 minus
What do you do?
We are taking a difference of sets.
HT. How do you calculate it?
We can take
1 minus
of.
probability of.
Okay. So let me write down the sets first. Probabilities, it's a vector. H, TT, TH. Let's try to translate this into English first. This is probability of what? Can we translate this into English?
We can't.
Or maybe this is easier if I did this one. Then what's this?
Probability that no coins,
Same
no
to-
coin is hedge.
Probability of
We are
not
not
having
having two
both
heads.
roles.
The probability that they are not both H, right? Okay. I'm not going to spend time to write it. And this, you can use this.
Second coin is head.
And this guy is Cartesian product of H times H. And then you can minus P1 H times P2 H, and this is 1 minus half times half, and 3/4. Okay. Again, I suppose you already know the answer before we look at all of this, right? Okay, so essentially, this is not, this doesn't give you all possibilities. This only give you A when A can be written as Cartesian product. Okay? But, and from this value, you can derive the probability of all the rest. What's the reason? How did you get all the rest? How did you get all the rest sets?
It's been forcing the
You obtain by complement and the union or intersection. Oops, we are 4 minutes over. Okay, so then you can use 1 minus and also the union and the intersection formula to calculate it. Okay? All right, let's stop here. I will email your homework today.
Grab that microphone from me. Do you need to save any of those files on this? Okay.
I'm done.
This is